السلام عليكم ورحمة الله وبركاته. أسعد الله أوقاتكم بكل خير. حضورنا الكريم، معكم جهينة الريامية من مجموعة الكيمياء بجامعة السلطان قابوس. شرفتونا اليوم في المحاضرة السابعة من محاضرات المجلس الكيميائي، ونبارك لكم جميع طلبة الجامعة عودتكم لصفوف الدراسة، عسى إن شاء الله كذا يكون عام مكلل بالنجاح وبالتوفيق. إن شاء الله معانا في محاضرة اليوم راح يكون الدكتور إسحاق النافعي. طبعا الدكتور إسحاق خريج قسم الكيمياء بجامعة السلطان قابوس عام 2011. عين أيضا معيد في نفس القسم في الفترة من عام 2013 ل 2000 في الفترة من عام 2011 ل 2013. أيضا حصل على شهادة الماجستير من الولايات المتحدة الأمريكية عام 2015. كان أيضا محاضر في قسم الكيمياء في عام 2015، وهو حاليا طالب دكتوراه في سنته الرابعة في جامعة مانشستر البريطانية، وعلى أمل إن شاء الله أن يتخرج في خريف 2021 ويلتحق بالقسم بإذن الله في ربيع 2022. ما شاء الله مسيرة الدكتور حافلة بالمعرفة والإنجازات العلمية. نرحب بك دكتورنا إسحاق، شرفتنا ونشكر تواجدك وقبولك للدعوة، ومتشوقين كذا نتعرف أكثر عن عنوان المحاضرة اللي هو كيمياء التآكل. طبعا كيمياء التآكل مفهوم يعبر عن التدهور الحاصل لخواص المادة الأساسية نتيجة لتفاعل كيميائي أو تفاعل إلكتروكيميائي مع البيئة الخارجية. وبإذن الله من خلال محاضرتنا اليوم إن شاء الله راح نتعرف على ماهية التآكل وهل يمكن إيقاف هذه المشكلة. أيضا راح نتعرف على أهم التقنيات الحديثة في منع هذه المشكلة، وإن شاء الله أشياء أخرى راح يقدمها دكتور إسحاق. تفضل دكتور، المايك معك.
السلام عليكم ورحمة الله وبركاته. شكرا جهينة على هذه المقدمة، يعني أسهلت كثير ما شاء الله. ليش؟ أول شيء أنتم مسوين في الإعلان دكتور، بس بعدني لسه ما دكتور، بس يعني مستعجلين علي شكلكم. شكرا جزيلا لكم على هذه الاستضافة. رجعتونا لجو المحاضرات بعد ما افتقدناه حوالي 3 سنوات من الحين. تمام. هو عنوان المحاضرة اليوم كان يفيد corrosion. طبعا بتكون باللغة الإنجليزية إن شاء الله، بس بين الفينة والأخرى يعني ممكن يعني عشان نسهل الحضور مثلا في بعض المصطلحات بالعربي إن شاء الله. تمام. Just let me share my screen. Can you see my screen? Can you confirm that, please?
Yes.
Thank you so much.
Yes.
Okay, so welcome everybody again. Today's lecture is about can we defeat corrosion? I mean, this is like a big word, corrosion. And to be honest, this subject or this word does not taken, I mean, that much in the chemistry department. There are only one course talk about corrosion in the department, which is elective course. But I think it's very important for all the chemistry student to study this subject. So today's lecture is just a quick overview of this subject, and it's not a reference. It's just like a quick overview of this subject. So throughout this lecture, I'm gonna give you an introduction about corrosion, types of corrosion, and then the main part is the corrosion chemistry, which is will contain the thermodynamics of corrosion, kinetics of corrosion, and then we'll move to the topic: can we stop corrosion, and is this a problem that can be stopped or mitigating? And then we'll take the electrochemical test to study corrosion. After that, I'll give you a recent advancement in corrosion prevention. So finally, I will give you a corrosion market and jobs in Oman. What is the jobs market of corrosion specialist in Oman? And finally, we conclude this lecture. So starting with the basic definition of corrosion, this word corrosion. So in its basic definition, corrosion is the spontaneous interaction of the metals and alloys with their environment, especially water and oxygen, which result in changing their properties and eventually deterioration and destruction of these materials. So first of all, corrosion is for, this word is for all metals. The rust is only for steel or for iron. So corrosion is a spontaneous. If we just take a look to this picture here, between non-spontaneous and spontaneous reactions. So spontaneous means تفاعل تلقائي, which is favorable by the environment. So if we have the ore at the beginning, which is the قام طبيعي, to produce a steel or other metals, we need to put some energy. So this is not as spontaneous. And then if we have a steel pipe or any metal pipe, then it's more stable to this pipe to come back to its natural state, which is oxides or sulfides. So the spontaneous means تلقائي, and it's very favorable by the environment. So we cannot stop corrosion, I mean, in theory, but in practice, we can slow down or mitigate this problem. It is a big problem. Why? So corrosion globally, it's a big problem because it includes loss of money and materials. And in USA alone, about 276 billions every year is loosened by corrosion. And if we can see here, the price of metals is increasingly increases over the years. So the loss of money and materials, and more importantly, also endangers life. If we can see here, this bridge in the USA is fallen because of the corrosion, and there is many catastrophic accidents in the USA, especially, that's taken a lot of lives. So it's a big problem, and maintenance should be taken regularly to avoid any bad consequences. So corrosion, there is a lot of types of corrosion, but the main types are these types here. We have uniform or general corrosion, we have galvanic corrosion, crevice corrosion, basic corrosion, intergranular corrosion, stress corrosion, cracking, filiform corrosion, erosion corrosion, and de-alloying. As I said before, these are only the main or the most famous types. There are many types like sweet corrosion, sour corrosion, and high temperature corrosion, and etc. We'll take these types of corrosion one by one, and starting by the uniform or general corrosion. This takes place equally throughout the metal surface. If you can see this chip here, it's corroded eventually in all its parts, so we call it this uniform or general corrosion. So the loss of metal is equally throughout this surface. Check your house. I'm sure that you will find an example, especially the old doors, which are the steel doors. You will see this type of corrosion. Then we have galvanic corrosion. This occurs between two different metals in contact with each other, like between zinc and iron in this photo here, or Cu, which is copper or iron. If you can see here, if two different metals in contact, the more active metal is corroded in favor of the low or lowest active metal. Then we have crevice corrosion. Crevice corrosion occurs due to geometrical restrictions in the metal structure, such as under gasket or seal or under bots here. So if we can see here, the narrow or the narrow area between these gasket here will initiate a corrosion cell by differentiation in the concentration of oxygen and also the humidity concentration, for example. So this will initiate a differential, or we call it differential corrosion cell, and the corrosion is started after that. The next type is, we call it pitting corrosion, and this is occur in very restricted areas. We can see it like pits there, which is like very narrow bits.
ليش ما تستخدمين أبوها طوشة ذكية ونازعت.
Can I continue, please? Thank you. So going back to the building corrosion, we can see here the bits are, this is like aluminum surface, and we have small bits there because of the breaking of the protective layer of aluminum oxide. So this is mainly occurs or produced by chloride ions. After that, we have intergranular corrosion, which occurs between grain boundaries inside the metal or alloy. This corrosion weakens the material and make it very easier to crack, even though it's not seen by the naked eye, but it's a microscopic, but it's very dangerous because it's weaken the material and make it easier to crack and destroy it after that. Then we have the stress corrosion cracking, which is propagates by applying stress due to the structure after initiation of corrosion by the environment in metal or alloy. So for example, if we have bits like bit corrosion here, these bits can initiate a stress corrosion cracking by applying a stress, and then the pipe or any structure can destroy it after that. Another corrosion form is filiform corrosion. This is happened only inside or underneath the coatings or paints. So if we have a coating or paints, sometimes we have like this structure here, which are mainly corrosion that taking places under the coating or under the paints. After that, we have erosion corrosion, which occurs due to a flow of liquids or fine materials. This type of corrosion mainly seen in pipes. For example, this picture here, in oil pipes or gas pipes, due to the flow of liquids or gases, this corrosion can be happen, and the protective material can be washed off, and the corrosion is started until the failure of all these structures. The final type here is the de-alloying or leaching of selective materials in alloys. Also, this is a microscopic materials. Imagine this was without any voids at the beginning, but if these voids was at the beginning, there are materials here, but after the dissolution or leaching of these materials, imagine that material will be just like a sponge, and it's be very easy to crack after that. So it's very dangerous also this time. Moving to the corrosion chemistry, which is the main part here of to study the corrosion. First of all, what's the corrosion? The components of corrosion cell. The corrosion to happen, it needs 4 main parts. We can see it here in this picture. The anodic area, which is the anode that where the metal corrodes and oxidize, and the cathodic part, which will be the same metal or another metal. That's where the cathodic reaction happens to balance the anodic reaction. And also for these 2 reactions to happen, we need an ionic bath in the electrolyte and an electronic bath, which is in the metals, to transfer the electrons and there to transfer the ions. So the main reactions, the main reaction in corrosion cell are oxidation at anode and reduction at cathode. So the oxidation reaction is always a metal that corroded. As we can see in this equation, the metal oxidation, it's oxide to produce metal ions, which in turn combine with hydrogen or oxygen or hydroxide to form the natural form of that metal. And the reduction reactions are oxygen reduction or hydrogen evolution in most of the cases of corrosion reactions. So the reduction reactions are mainly these 2 are the oxygen reduction reactions, and the final one is the hydrogen evolution reaction. Taking an example just to demonstrate these equations here, imagine that we have zinc in 3.5% NaCl solution. A 3.5% NaCl solution means that in 1 liter of NaCl solution, or in 1 liter of distilled water, we have 3.5 grams of NaCl solution. That will produce a 3.5% NaCl solution, which is, if you measure the pH, is close to the neutral of pH around 7. So in this situation, there is no, it's not acidic, so there is no H plus there. So the oxidation reaction is zinc oxidation. So zinc dissolved to produce zinc 2 plus 2 electrons. And in turn, these 2 electrons are consumed to produce the hydroxide by oxygen reduction. So of course, this will be to balance these 2 reactions. We have 2 zinc here to produce 4 electrons that are consumed by the O2 and H2O to produce the OH2. So the overall reaction here is producing the zinc hydroxide, which is the natural form that can be found in the nature. But imagine this reaction, we put the zinc now in the hydrochloric acid with a pH less than 7. So we have a lot of H2. So now the reduction reaction, the oxidation reaction is always the zinc oxidation, but the reduction reaction here will be the 2H plus 2 electrons. So the 2 electrons here consumed by the protons to produce hydrogen gas, which is the hydrogen evolution reaction in this side. This is the picture just to demonstrate these 2 reactions with the HCl solution. So the zinc dissolve or corrode, and then the 2 electrons are consumed by the protons to produce H plus. And if you put a zinc in HCl, you will see the hydrogen bubbles come outside, which is demonstrate the hydrogen evolution. Now moving to the standard electrode potential at 20, or the standard means at 25 degrees Celsius. The standard electrode potential, also called the electromotive force, is the property of each element written in a half reduction reaction. If you can see here, all these metals or elements are written in half reduction reaction. So if we have more positive standard electrode potential, that means it's more noble, the metal or the material. And as you can see here, gold is the most noble, that's hardly go on any corrosion, even if you just lift for hundreds of years. On the other hand, for more negative one, that means the more active the elements. And also you can see here the lithium is the most active elements. That means it corroded the fast, or reactive the faster. So these values here are used in the corrosion thermodynamics, such as Nernst equation, to determine whether if a combination of two metals, which one will corrode if we combine these 2 metals. For example, in galvanic corrosion, which 2 metals is corroded. We can see, or we will see that in just in few minutes. So moving to just a quick equations of Nernst equation, which is related to the thermodynamics of corrosion for an electrochemical reaction here. Imagine this is like a theoretical reaction here, but you can imagine as the zinc corrosion reaction with some relation and math using the equilibrium reaction, equilibrium equation, we can find these 2 elements. I mean, this lecture is not to found this equation or to find these equations or related this equation, just to give you overview of how we relate the equation with the corrosion. So we have the final equation, we call it Nernst equation. What's the benefit of this equation? The benefit is to calculate the non-standard corrosion potential. Here we have the standard electrode potential. By this equation, you can calculate the non-standard corrosion electrode potential. So, for example, this is a standard with 25 degrees Celsius and a unity concentration, which is 1 molar. But here, with different concentrations of all of these, you can calculate the standard electrode potential or the electrode potential by using the standard one. This E naught here is from the table, and the concentrations of any of these ions here, we can use it. The N here is the number of electrons, and from this we can calculate the electrode potential of each electrode, either the anode or the cathode, and after that we can determine whether this corrosion cell will proceed or not proceed. So here the corrosion thermodynamics. So the thermodynamics of corrosion only gives you the quick answer of whether this metal will corrode or not. So it just only says yes or no without telling anything about how fast the reaction or how fast the corrosion of that metal. So for example, if we have this corrosion cell here between copper and zinc, okay, with these two standard electrode potential, and the question here, if we have this corrosion cell, which one of these metals will corrode if one of them can corrode? So to determine this, we need the equation here to calculate the E cathode and E anode. So we have the anode and the cathode here, and then we calculate each of them. So we calculate E cathode and E anode with the concentrations by using this equation here. And then, so here, this is the E cathode or E anode. This E naught is these values here. And after finding the E cathode and E anode, we can calculate the E cell, which is E cathode minus E anode. Okay. After that, we use the E cell in the equation. This the thermodynamic equation here, which is delta E, which is the Gibbs energy, equal to NF E cell. N here is the number of electrons in the equation or in the reaction. F is the Faraday constant, and E is the E cell that we calculated here. So if this equation gives you a positive number, that's mean it's non-spontaneous reaction. So there is no corrosion will happen here, and this reaction will not proceed. On the other hand, if this gives you a negative number, that means a spontaneous reaction and the corrosion is taking place with the anode, which is the zinc. Okay. Another thermodynamics useful equations or diagrams in corrosion science is the diagrams, we call it Borbet diagrams. I hope you see this before. It's a very useful diagrams in corrosion science and metallurgy and hydrometallurgy. So metallurgy is تعدين المتعدين, and hydrometallurgy is استخلاص المعادن. So these diagrams are very helpful in corrosion science especially. So these diagrams are comprehensive diagrams of E, which is الشحنة, versus the BH, which show the stability relation in aqueous system. So these diagrams can give you indication where specific metals or alloy can corrode, but no information about the rate. Again, here thermodynamics is only about yes or no, without giving any numbers of the rate or the speed of the reactions. These Borbet diagrams can be drawn by Nernst equation, by this equation here, and with another relation, which is equilibrium relations, to draw each one of these lines. Okay, so by this reaction here, for example, zinc and zinc 2+, by this reaction, which is oxidation of zinc to zinc plus, by some relation, we can find where this line is, whether here or there. Okay, but it's here. If you just draw it by yourself, you can draw it here. But more easily now, we have many softwares that you can do this just in one click by providing the concentrations, the pressure and temperature of the system. So these diagrams here can give you just in a glance that where the metal can corrode or where the metal is passivating or where the metal is immune to corrosion. Take, for example, this, whether this or that. So for this, which is for iron, at this one here, FES, we call it this immunity. That's mean in this potential here in all the pH range in this area here, the Fe is immune to corrosion. It cannot corrode. But if the potential is increasing above minus 0.44, which is the E naught for iron, it will corrode to produce Fe2. And if the potential increases a lot, it produces Fe3+. On the other hand, if this here, in increasing the pH, so at pH 4, for example, it produces Fe2. But at pH 8, it will produce, at this point, for example, it will produce the Fe2O3, which is iron oxide, but this oxide is not protective. So, okay. Taking for zinc, for example, if we have this, if we have zinc in all this area here with the pH range and the potential, zinc is corroded. But here it's not corroded. Here again, it's corroded. More clear, these diagrams can be seen in aluminum diagrams. So for example, we take this aluminum 4-bay diagrams. It can tell you where aluminum is not corroded and where aluminum can be corroded. So here is the immunity. Here is the corrosion of aluminum. Here is the corrosion of aluminum. And here is the passivation of aluminum. Passivation means that there is a small or invisible oxide layer that cover the metal surface and protect it from any corrosion. We can see the demonstration of this passivation by seeing this video. I hope it this video explains the passivation, which is the invisible protective layer of metal oxide. In that video is iron oxide, but if you take example here in this diagram is the passivation of aluminum. This region here is the basis of the use of aluminum in many applications like airplanes and many structures, because at the neutral pH, which is from around 4 to 8.5, the aluminum is passivating. That means it's protected by an invisible oxide layer that makes it very strong, and it can resist the corrosion. But once that protective layer is scratched, it can also form again. But imagine that we change the pH of the aluminum here to more basic or more acidic, it will corrode eventually to produce aluminum oxide here or aluminum ions. So this passivation can protect many metals like chromium or aluminum, but not all the passivation is strong. For example, if we can see here, again, this is here like a passive layers for iron, but these are not strong. That's why we see rust on iron, but not in for example, in aluminum or in chromium. So this is the benefit of Borbé diagrams. We call Borbé, it's not Borbé-X, it's Borbé without mention of, without the X. So it's very useful to use this one, okay? It just give you a small, a quick glance where the metal will corrode or where the metal is not corroded. So we did the thermodynamics, now the kinetics. Remember, again, I just remind you, this is only a quick lecture without taking the math very seriously here. Okay, just a quick one without making you boring with all the equations, just a quick one. So the kinetics here tells you how the fast the reaction is. So thermodynamics tell you whether the action will proceed or not. It's yes or no. But on the other hand, kinetics tell you how fast the reaction or how fast the corrosion is. It will give you an exact numbers of the corrosion rates in different units, as you can see here. So it gives you the kinetics here mainly in current density. So this weight loss or penetration is mainly used without any equations or any devices. It's just a very initiative or very primary experiments. But for electrochemical test, it gives you with the current density by centimeter, which is done by the kinetics. So the kinetics are where the math puts its nose in corrosion science. We know that math is very jealous and it wants to enter any science. So in corrosion science, math enter through the kinetics of corrosion. So the corrosion rates can be determined without equations, as I said before, by non-electrochemical techniques like loose weighting experiment, and it gives you the gram per centimeter per hour or per day. But the kinetics give you the corrosion rate by microampere or milliampere or ampere per centimeter or meter square. So with electrochemical techniques, which is more accurate recently, equations are needed as follows. I mean, before this equation, maybe 2 papers of integration to find this equation here, which is called the Butler-Volmer equation. It gives you 2 parts. One is for anode and one is for cathode, or one for anodic reaction and the other is for cathodic reaction. The I net here, which is the corrosion rate, the net corrosion rate, and the I not here is the corrosion current, yes, or the exchange current density. And I said before, the evolution of this equation is out of this lecture scope, just to give you that corrosion kinetics have many equations, and all of these equations are tend to produce or to gives you the corrosion rate in exact numbers of any metals or alloys. So corrosion kinetics, before just take deep in corrosion kinetics, some definition needs to be understood. The first one is polarization. And I have here two polarization. One is the anodic polarization. Imagine here, this is the corrosion potential here. So if we polarize a metal cathodically, for example, that means it's the displacement of electrode potential. So this is the electrode potential here. This is the current density. So the metal is here in the stable state or in the OCB state. So if we polarize cathodically, that means we displace the electrode potential to the down to the cathodic part, to the negative direction. On the other hand, if we have anodic polarization, that means we displace the corrosion or the electrode potential to the positive direction. From these two, the polarization, we can get a tafel plot or what we call it Evans plot, which we can see it later. And from this plot, we can calculate the corrosion rate and potential of the corrosion, current of the corrosion, and also the slopes of the tafel slopes. So this is the polarization, current, and the current density in ampere or microampere. Here is the current density, and potential in volt. So in corrosion science, these two electrical definitions are more important. The electrode potential, الشحنة الكهربائية, and the current or current density, which is the تيار كهربائي in amperes, and the potential always in volt or millivolt. So now the big question, can we stop corrosion? The short answer is no. So what we can do? If you remember at the beginning, I said that the corrosion cell have four main parts, which is the cathode, the anode, the ionic connection, and the electrical or the electronic connection. To stop the corrosion or slow down the corrosion, we need to slow down one of these four components or remove one of it. So there are several methods used to slow or mitigate corrosion, such as corrosion, cathodic protection, anodic protection, inhibitors, and coatings. We'll take each one deeply. The first one is cathodic protection. So the cathodic protection is used to protect the metal by converting them to cathodes in electrochemical corrosion cell by sacrificial anodes or by applying current from outside source to the metal. So, for example, the sacrificial anodes here is usually made with steel and zinc. So, if we go back to here, we can see zinc is minus 0.76, and we can see iron is minus 0.447. So zinc is more active than iron. So if we attach zinc and iron, that means zinc will corrode and iron will not. So this sacrificial protection here, the sacrificial anodes mainly used with zinc, aluminum, or magnesium. That's mainly attached to the steel structures. And so these will act as anodes and corrode in preference of the cathode, which is the steel substrate. So we can protect the steel substrate by adding these sacrificial anodes. We call it cathodic protection. Or on the other hand, we can apply empressed current. So we just add electrons to the steel substrate that it cannot lose any electrons, and the oxidation of the steel will not happen. So this is one type of slowing down the corrosion reaction. The other one is the anodic protection. So the anodic protection involves shifting the potential to higher values in order to reach passivation. If you just take a look to the Borbet diagrams here, we can see we can push the the metal to passive region. That means it's passivating and the active it's protected by the passive layer. But unfortunately, this protection is only applicable for metals that can form active-passive transition, not all metals. And it can be applied by applying embraced potential. So for example, here, for chromium, imagine the chromium is here. We can push it outside to the passive to produce a passive layer of chromium, and also for titanium, for example. So this is used, but not as wide as the cathodic protection. The other one is inhibitors. So inhibitors are chemicals that prevent the corrosion by controlling the metal dissolution and forming protective films that protect the steel or any other metal surface. There are many inhibitors like anodic inhibitors, cathodic inhibitors, organic inhibitors, precipitation inhibitors, ohmic inhibitors, and vapor phase inhibitors. But the most used or most famous inhibitor was the chromate, which is now not used due to the toxicity, and molybdate phosphate. So the chromate was the very best chemical inhibitors that ever produced. But unfortunately, due to the toxicity of chromium-6, it's now banned and cannot produce. So the research now tried to form molybdate and phosphate. But the drawbacks are the cost and environmental concerns of these corrosion inhibitors. The other type of corrosion prevention is coatings, which is the famous or more easiest method. These coatings can be organic, such as epoxy paints. Organics here is just the paints. Inorganic, such as silicate paints, again, it's a paint, or metallic, such as galvanized steel. So that is steel covered by zinc coating. You can see this galvanized steel in the roads. It's used in the roads a lot, which is the barrier of the roads. Now we just take a quick overview of the electrochemical test to study corrosion in the lab. So to run an electrochemical test to study corrosion, you need to set up a corrosion cell or electrochemical cell. And that must include the reference electrode, which is normally silver chloride, or calomel electrode, and counter or auxiliary electrode, which is platinum or graphite. This electrode only to close the circuit, the electrical circuit. And then the working electrode, which is the metal in test. And we have a potentiostat, which is the device for electrochemical test, like this one. I'm sure you can see it in the physical lab. In the physical lab, if you study Chem 333 or Chem 4433. And the electrolyte solution, which is normally NaCl solution for the basic experiment. We use a lot of NaCl because it's mimic the solutions, especially in marine environments. So this is what you need to run a test. So the electrochemical test started with OCP versus time. The OCP stands for open circuit potential. This open circuit potential is the potential where there is no current flowing, i.e. no corrosion. So for example, this is for aluminum here. It's around 85 minus 0.85. So you did this test to find where is the OCP of the test of the material. Okay. If you have coatings, for example, or two different metals, you can test this one to see at what time the corrosion is started for each metal. So it's very important and very basic experiment. You can do it by potentiostat or just by ammeter without a potentiostat. Then we have the polarization, which is one of the main or the most important experiments, which allows you to determine the corrosion rate, study the behaviors of corrosion reactions and passivity. For example, if I did this myself, which is a steel in carbonate solution, you can see here where is the cathodic reaction, whether it's oxygen reduction or hydrogen evolution. Hydrogen evolution is normally flat, but oxygen reduction is normally vertical. So you can see whether the reduction reaction is oxygen reduction or hydrogen evolution. And then you can see the steel corrosion or the metal corrosion. And if there is a passivity, you can see it clearly in this polarization test. And again here, the axes are here potential, which is millivolt versus AgCl, and log I, which is the current density. Again, from polarization by Tafel extrapolation. So you have like, from experiment, you have like these two diagrams. By practical, you can extrapolate, making a line here and making a line there to make it an X, and to find the corrosion potential and the corrosion current density. From corrosion current density, you can calculate the corrosion rate. And from the slopes of the Tafel slope, this Tafel slope for the anodic and for the cathodic, you can calculate the corrosion rate again. Okay, and not to forget that the upper part, the more positive part is the anodic part, and the less or the more negative part is the anodic or the cathodic part. Okay, then we have linear polarization resistance. In this experiment, the potential versus current, again, potential versus current is not a log current. Here we have a log current. Here we have a log current, but here is a current in microampere and potential. If you see here, the range of the potential is very wide, maybe more than 1000 millivolt. But for LBR, it's very narrow, usually less than 20 millivolt to get a linear measurements. From that linear measurement, we can calculate the slope. And from that slope, we have what we call it polarization resistance, which is related to the corrosion rate. So if we have the corrosion, the resistance, the polarization resistance, we can calculate the corrosion rate again in numbers. Okay, so so the OCB gives you the time usually where the metals fail, or what is the OCB of the test. The polarization and the LBR gives you the exact number of the corrosion rate if you need it. And the third one is the electrochemical impedance spectroscopy. This is all the previous one, which is OCB, polarization, and LBR, uses direct current, which is give you resistance. But for electrochemical impedance, impedance is the opposite of, it's not the opposite, it's just like acronym of resistance, but in alternating current, not direct current. So the current here, we have it like that, okay, not a direct one. But this test is usually or most used in testing the performance of coating protection, to give you the resistances of the solution, of the coating, of the metal, and the double layer capacitance of the whole system. Okay, so there is no corrosion rates out. You can calculate from this experiment. Now, the recent advancements in corrosion prevention, organic coatings or the paints, الأصباغ حاليا, are the most used method for corrosion prevention because of their advantages such as low relative price and the easiness to apply and easiness also to maintain. So, but the recent advancement in corrosion prevention aims to develop more resistive and protective paints. You can see here what we call zinc-rich coatings. Imagine this is a paint. So it's just a normal paint which is full of zinc powder. And this is one of the most used paints in nowadays, especially in marine structures. And why is that? Because it's offer the sacrificial protection by zinc to protect the steel. So if there is a scratch in the paints, the zinc will react as an anode, and it's dissolved or corrode and protect the steel substrate. But the problem is that when the zinc is disconnected from each other or from the steel substrate, it cannot offer any protection to the steel substrate. But from the corrosion product of zinc and iron, this paint or this coating can offer the barrier effect or the barrier properties of this coating, and inhibit or delay the ingress of water and oxygen. So it may protect the structure up to 15, 20, or 30 years in some cases. So the very recent advancements in zinc-rich coatings are by adding more conductive pigments, such as graphene. They try now with graphene, carbon black, carbon nanotubes, nano alumina, and nano titania. So if we have, for example, parts of graphene or carbon nanotubes, they suggest that adding these pigments will enhance the connection between the zinc particles. That means it's prolong or take a long time for zinc to disconnect and offer a lot or more protective to the steel substrates. Okay, but unfortunately it's not proven yet. The mechanism of this protection is not proven, because as we know, if we go back to the electrode potential, the carbon is very cathodic in comparison, which is more stable in comparison with steel and zinc itself. So imagine if there is a cell, a corrosion cell between graphene or carbon and steel, the steel will corrode it faster than before. So this research is recently is of interest, but the exact mechanism are not well understood. So currently my PhD project is concentrating on this subject here, which is adding, this is my own photo here, is concentrating on what will happen if we add aluminum and graphite or graphene oxide to the zinc-rich coatings, and what is happening. Does this will enhance the corrosion protection, or in other hand can destroy the steel substrate? So it's a big project, and it's need a lot of effort and a lot of equipments. But unfortunately, due to this coronavirus, now we stopped for nearly 6 months and hope to go back to the work soon, inshallah. Okay. Now, despite the recent research and effort to prevent corrosion, there is no magic solution to stop the corrosion phenomena, unfortunately. But provide the time scale for any structure, some paints can protect the structure for more than 30 years if it remains mechanically intact, especially in the marine structures. We concentrate on the marine structure because marine structure is very aggressive environment because of the salts, humidity, oxygen, and the high concentration of humidity. So this is just an overview of corrosion advancements recently. Now we just move to corrosion market and jobs of corrosion scientists in Oman. First of all, the corrosion course in the Department of Chemistry is offered just once a year, which is Chem 3337, Fundamentals of Corrosion Metals. It's a departmental elective course, as I said, given once a year. I think this semester is given. But nevertheless, topics in corrosion can be encountered in general chemistry, physical chemistry, and materials chemistry courses. And this book is what is taught. It's a very interesting book, and I advise everyone that who interested in corrosion science to read this book. It's very easy, very useful book in corrosion science. Okay, so jobs in Oman for the corrosion scientist. The chemist should meet well with corrosion jobs, since corrosion basics and prevention rely on chemistry. Nowadays, many engineering sectors try to call it corrosion engineering, not corrosion science. Some of them say corrosion engineering and science, but basically it's science, not engineering. Engineering only for the application, but you need the basics first. So a chemist should meet well with the corrosion jobs, okay? Even if you don't have a background, because of your chemistry background, you can fit well with these jobs, not left for engineering graduate, okay? Because you have the basic, which is the main important. So normally corrosion jobs are needed mainly in oil and gas industries and refineries, because we don't have that much companies or energy companies. We have only oil and gas and refineries. These corrosion are mainly required in oil and gas companies and refineries. For example, the BDO and Oman Oil, I have friends of mine, they are working on the corrosion jobs here. They are a chemistry graduate and they work in corrosion, especially in corrosion jobs. And refineries, if you just take a look to Musfat Duqm, it's a huge metallic structure and it needs a lot of corrosion maintenance and corrosion maintenance and what you call it متابعة. يعني ايش نسيت حتى بالانجليزي. المهم okay, so finally I just want to conclude this lecture. First of all, I just make it a very short lecture to not get you bored of this subject, and it's very short overview with everything. So a very short overview of corrosion science, a very short overview of corrosion chemistry, corrosion thermodynamics, corrosion kinetics, and electrochemical corrosion and recent advancements. So it's a very short overview of the fundamentals. And I hope that you find corrosion science is an interesting subject that can be seen well in everyday life. So I want from you now, for example, tomorrow, just take a look around your house, for example, and see what type of corrosion can you have in your house. I'm sure that you will find at least 2 types of corrosion in your house, okay? So despite many corrosion prevention methods, corrosion still exists as a big problem, okay? And there are many test and characterization techniques to study corrosion, whether in the labs or in the companies or in the field. There are many tests that I cannot cover here. I just covered the basics of the corrosion test. The anti-corrosion methods are developed every day with new advances. If you can have access to the scientific journals, you can enter the corrosion science journal and see what's the development in corrosion science every day. So in Oman, corrosion jobs can be found in oil and gas industry and refineries. As I said before, you are a chemist, you are very capable, or you fit well with these jobs, okay? Finally, can we defeat corrosion? The short answer is no, but provided the time scale of any structure, there will be a big chance to defeat it. For example, imagine that we have a car, we want it just for 15 years, and so there is a good chance we can defeat the corrosion these 15 years, but by a good paint, okay? And you can see it now for the cars, it's hardly corroded over this time of its life, okay? So this is all what I have today, and thank you all, and thank you for chemistry group to have me in this lecturing here, okay? And you can, if you need anything, you can reach me through my university email at alnafai@sq.edu or through my Twitter account. This is my account. شكرا جزيلا مرة ثانية للكيمستري جروب على الاستضافة، جزاكم الله خير. شكر موصول للأعضاء والمنظمين وجميع من حضر، شكرا جزيلا لكم. إذا عندكم أي استفسار تفضلوا سواء الحين أو ترسلوا في الإيميل.
شكرا لك جزيلا، شكرا أستاذ إسحاق، ما قصرت. حقيقي كانت المحاضرة جدا ممتعة ومثرية، يعطيك العافية. فننتقل معك دكتورنا الحين مع فقرة الاستفسارات، وأي أحد مع أي استفسار أو أي سؤال أو أي إضافة ممكن أنه يطرحها على الدكتور إسحاق. راح نقفل الشات ونستقبل استفساراتكم على الرابط الموجود في الشات، بس فقط يعني بإمكانكم أنكم تدخلوا الكود، واللي عنده أي استفسار.
السلام عليكم دكتور إسحاق.
عليكم السلام ورحمة الله.
معك عبد العزيز بني عرابة.
حياك الله عبد العزيز.
كيف أمورك؟
الحمد لله طيب.
يعني first of all I would like to thank you for this small presentation or lecture. In general, corrosion is a very big subject. I have been working with the corrosion, but with inhibitor side in oil and gas field for the past few years. But it's a big topic once it's come, for example, selection of the inhibitor, the way you are monitoring the inhibitor performance, corrosion rate in the system. There is also prediction modeling. You can use it by putting the system parameter on that model, and then it will give you an indication on what is the corrosion rate will be in the system. Also, there is too many ways to monitoring the corrosion in the system using couple of method like coupons, side stream. I don't know if you have been working on that previously. So in general, corrosion is very big, and it's case by case. For any case, it's not the general. You cannot, from direct information you can get to know this is okay, this is general corrosion, or this is let's say H2S or whatever. So yeah, so this is what I want to say on the market. I think all of the oil gas company, they do have opportunity for the corrosions, and because it's directly impact the production side. If you have any corrosion in the system, of course your production will be reduced, and also if there is a big failures that the capex, you need to invest in the capex, so you have to protect your plant or your station, pipelines, whatever, from corrosion, because it's directly affecting your system. Exactly. And it's by the end of the day is the production of oil, so it is key topic.
Yes, thank you Abdulaziz, thank you for this information. I mean, you are an expert on this. Yeah, as I said, corrosion science is a very big subject. Is not that even a semester cannot cover all of this. So for example, the corrosion course for one semester is not enough either. Just give you the equations and the relative occurrence or the types of corrosion. But practically, even though in the lab or in the field, is very different. So you encounter this in the field, in the company, and you see it's not just an easy or a direct equations or science. It needs a lot of experience and training before to know what is the problem exactly, right?
Yes.
Yeah, so but I mean, in the university we teach the basics, so after that the graduate can build their own expertise and and search for itself, and for example continue the higher education, master in corrosion science, then the PhD in corrosion science. But even though, if you, for example, in my PhD now, I just study the coatings, which is the paints, how to protect the steel pipes or the steel structures. So I don't know anything about the soil corrosion, or for example the bitter corrosion or the high temperature corrosion. So it's a very wide subject that needs to everybody, if you want something, just concentrate on that. But in general, it's good. I mean, for the bachelor students or the bachelor degree, a corrosion science course is enough to just give you the wide image or the wide overview of this, like many subjects. Thank you, Abdulaziz, for the
even for this LPR. I mean, this common test, it's used even in oil and gas, especially with the service company. But also there is another couple of tests also involved, because the LPR is only for the static condition. There is no pressure or temperature involved. There is another test called I think rotating something like that. Rotating cylinder electrode. Use it for the
electrode.
Yeah.
Thank you.
Okay, thank you, doctor.
Thank you so much. Thank you. تمام. اللي عنده فكرة المشروع ممكن بعدين إن شاء الله على إيميلي. أهم شيء يكون معي لي نسبة من المشروع.
أنا عندي فكرة مشروع حالك دكتور.
خلاص.
في بعض الشركات بدأت تشتغل على اللي هو يعملوا coating inside the carbon steel. يعني في العادة شركات مثلا المانيفولد big pipes يستعملوا كربون ستيل ولا whatever. ففي بعض الشركات بدأت تعمل اللي يسميه بي لاين، اللي هو عندك لاين كربون ستيل بس من داخل انت عامل له coating with ما اعرف heavy plastic او حاجة كذا او بوليمر or whatever. ايوه
ايبوكسي. ايوه
هو صح انه it's quite expensive but for long term is a good option.
It's a good option, but again the problem is
if you have anything
the mechanical failure. If you have a mechanical failure, for example scratch or something, you cannot detect it. Yeah. إن شاء الله.
دكتور عندي سؤال. في خلال دراستك الحين في أي برودكشن موديلينج تستعمله؟ to identify في بعض يعني مثلا في الجامعات الكبيرة في US أو ما أدري وين، بس يعني مثلا نحن كشركة عندنا مثلا ديل مع شركة في US هي اللي تعمل prediction modeling. يعني مثل السوفت وير نحن يعني what we need to provide them or just only يعني مثلا البروسيس بارامتر مثلا يعني diameter of the pipeline, how much the CO2 in the system, how much the H2S in the system, what is the brine of the water inside the system, something like that. يعني have you come across on those prediction modeling or not yet?
No, not yet.
Okay.
Yeah.
طيب شكرا دكتور إسحاق، يعطيك العافية. ما قصرت.
شكرا جزيلا، ما قصرتوا أنتم، جزاكم الله خير على الاستضافة. رجعتونا لجو المحاضرات ونفس الشيء لجو الكيمستري جروب بشكل عام، كنا فيها إداريين من 2008 إلى 2011. فشكرا جزيلا لكم.
ما شاء الله، شكرا جزيلا. انتهت فقرة الأسئلة حضورنا الكريم، بننتقل معاكم لفقرة شكر الداعمين، واللي دائما ما ننسى إن نشكرهم على دعمهم لجميع محاضرات المجلس. نتمنى منكم حضورنا إنكم ما تقصروا معاهم في المتابعة. وأول داعمينا معانا بإذن الله، أول داعمينا مشتل الزيزفون، مختصين بتوفير الشتلات النادرة والمحلية. كذلك معانا متجر إرث للمستلزمات الرجالية، يوفروا معانا مصار وكميم وغيرها من المستلزمات. أيضا متجر كوش، معانا متجر كوش للأحذية والشنط. كذلك متجر واي ستور، يوفروا الأشياء المميزة المستوردة من الخارج. أيضا متجر F4 كلوك، متجر إلكتروني، يوفروا ساعات ومحافظ بأسعار تنافسية وجودة عالية. أيضاً معنا متجر المترفة ماركة للهدايا وبيع العطور. كذلك متجر دايموند للأساور المصنوعة يدوياً. أيضاً معنا متجر متنفس لبيع كفرات الهواتف وغيرها من الأشياء الجميلة. شكرا لجميع داعمينا، وشكر خاص للدكتور إسحاق ولكم حضورنا الكريم. ننتقل معكم لآخر فقرة وهي فقرة السحب. طبعا مثل ما عودناكم راح يكون معانا 3 فائزين، راح نختارهم عشوائيا من المسجلين في قائمة الحضور، وراح يحصلوا على هدايا جميلة من الداعمين اللي ذكرناهم سابقا. ونبدأ بإذن الله نسحب على أول رابح. نشوف من راح يكون حليف الحظ بإذن الله اليوم. مبارك لي حميد راشد المقبالي، ألف ألف مبروك. نسحب على ثاني فائز. أنوار السعيد، ألف مبارك لك يا أنوار. نشوف ثالث فائز معانا لمحاضرتنا لليوم، عثمان العزري، مبارك لك يا عثمان. مبارك لكم فائزين محاضرة اليوم، ومبارك لكم جميعا بالمعلومات المثرية. وشكرا للجميع، وشكرا لك دكتور إسحاق، شرفتنا. نلتقيكم بإذن الله في محاضرات أخرى، وفي أمان الله.